That dowel is stubborn. Okay. Should be in good shape. Now, you'll probably lose some pieces, but don't really care, right? Ho ho ho. Da, 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 da. That is freaking cool. This is what we came to see. That is freaking amazing. So it's not just a couple steel belts, it's a lot of them. So the screws that were in there actually, like I thought, were bearing retainers. These big roller bearings. They're just kind of plates. So we'll take this out. I wonder what this is. Some kind of plastic piece. But wow, that sheared clean off right there. I'm wondering if we clean everything out, if we can put a new belt on here, salvage this thing. Wouldn't that be pretty awesome? Now what I want to explore is the actual mechanism that varies these ratios. That would be really, really awesome to understand how this thing works. Alright, time for some analysis here. First of all, I can't believe this thing made it 186,000 miles. All that torque is transmitted through these steel belts with these little segments, you know, sandwiched in between them. That is some really crazy engineering that they can make this thing actually work. I'm impressed. You know, you can't say that it's poor engineering. I mean, it did blow up, but the fact that it did go that far, yeah, that's impressive. Now, if you were towing a trailer with this or doing something heavy duty, I don't know. I would not trust this contraption. Or doing like a long cross-country trip into middle of nowhere, towing a trailer up, you know, the Rocky Mountains or something. So, first, what is this thing? So when you put the vehicle in park, this comes all the way up. Now what does it push on? It pushes on this guy right here. Kind of goes in here, and that extends this little pawl. And that engages into one of these teeth. And this secondary pulley is actually directly attached to the final drive. Okay? And it's jamming up because the belt's freaking destroyed. So it looks like there's a direct connection between the secondary pulley and the final drive. So when that pawl engages, you're in park and the vehicle won't move. So that is our park pawl engagement mechanism. So we got that out of the way. Now, how do these gear ratios vary? That's the heart of the CVT transmission. So maybe I'll clean up this mess a little bit here, and then we'll see how the heck these pulleys actually vary the gear ratio. So now that we see the carnage in here, the question arises, was it the belt that failed? Well, obviously it failed, but did it fail just from wear and tear and fatigue? Or did something actually cause it to fail? And to answer that question, we need to see how this transmission works, how the gear ratios vary, and what other failure could potentially cause this belt to, you know, either get overstressed or stretched. Because just looking at this, I mean, it's hard to say after the fact, but these steel bands, there's like, you know, 10 bands and there are two sets of them, what are the chances that they just break all at once, just from fatigue, in one spot? You can actually tell a surprising amount about a system just by looking at it, observing it. So what do we see right here? We see these two pulleys, the primary pulley and the secondary pulley, and the belt rides in these grooves, kind of like double cones opposed. So these concentric pulleys, right? For the gear ratio to vary, we'll draw this up on the whiteboard, but the belt has to ride either further in on the primary pulley or further in on the secondary pulley. And how do we get the belt, to go further in? Well, these pulleys actually change the distance between these cones. So then it lets the belt slip further in, and at the same time, the other pulley has to close the gap between the cones so the belt rides further out. So it looks like, for example, on the secondary pulley, this part is stationary with respect to the surface. However, the bottom part is the one that moves up and down. On the primary pulley, it's the opposite. I think the bottom surface stays stationary with respect to the transmission case, and this upper part moves in and out. Now, the reason I ask, did one of the pulleys fail and cause the belt to rip, is because right here you see another part of carnage. What the heck is this thing? Well, if you look close, inside the gap right here, you can see the leftovers of this guy in between the drum and the, I don't know what you want to call it. It's the outside and the inside. So that is supposed to be a seal all the way around. And right there it stops, so apparently this seal just got blown out when this pulley collapsed. Now, did it collapse because the belt ripped first? Or did the collapsing pulley overstretch the belt and cause the belt to rip? That, I'm afraid, we can't really answer. All I know is that it's not just the belt that failed, it's also the seal that got destroyed. And the material of the seal, I don't know if it's supposed to be pliable rubber, but this feels really stiff. And if you bend it, it'll probably crack. So, my question is, did the seal just get hardened over time from heat and lost its pliability and then just failed? The pressure got lost in the pulley collapsed, that pinched the belt and stretched it out and just ripped it. So it could be a failure of the pulley causing the belt to rip, or the belt ripping first, causing the pulley to collapse and blowing the seal. So what came first, the chicken or the egg? I'm not sure, but I wanted to draw up on the whiteboard exactly what I was talking about with these, with the distance between these two cones changing and how the gear ratio actually varies. So from all data in this component description, if we look at primary pulley, secondary pulley, steel belt, so read that little paragraph, composed of a pair of pulleys, the groove width is changed freely in the axial direction, and the steel belt, the steel star wheels are placed continuously, and the belt is guided with the multi-layer steel rings on both sides. Those are the bands that snapped. The groove width changes according to wrapping radius of the steel belt and pulley from the low status to overdrive status, continuously with non-step. It is controlled with the oil pressures of primary pulley and secondary pulley. So, oil pressures are key here. So let's drop a little schematic on the whiteboard. So the principle here, we have two axes, primary and secondary. So let's just draw a dotted line So this is going to be engine speed, or primary. And then our second axis is, to the wheels. And this is secondary. Okay. So first let's draw the configuration for, this is when you're just accelerating, this is like first gear. So low ratio. So in first gear, what happens? The engine spins fast and the wheels spin slow. And if you think about a bicycle, the pulley in the front is going to be small and the pulley in the back is going to be large to get that really low gear ratio. So the cone in the front small gear, right? So this cone is going to be spread out, and the cone in the back, again, we need to line up our center marks, is going to be squeezed in. Right? So then the belt, let's say the belt has this shape. If you bring that shape down here, it's actually going to ride up high on the secondary pulley. You see that? So the actual diameter on the primary side will be small, and the diameter on the secondary side will be large. So that's our first gear, or low gear. Now as this CVT does its thing and these cones move in and out, once we get to high gear, so this is like overdrive or high, the primary pulley actually gets squeezed in, and keep drawing this line down here. Our secondary pulley is actually going to come out. So now our belt will look something like this. It'll ride high on the primary side, and it'll be way down here on the secondary side. So you can see that this distance got big and this distance got small. That's your high gear ratio. The engine's spinning here, and for every engine revolution you'll get a lot more secondary pulley revolutions, and your wheels will go faster for the same engine speed. So I think that's pretty neat. The question is, if a pulley did collapse, which one was it? And since only one side moves, are these pulleys aligned at the moment? So as we saw on our transmission, this side of the secondary pulley is fixed, just draw it as a triangle, and this side of the primary pulley is fixed. So that means this guy can go in and out, And this guy on this side can go in and out. And keep in mind, the belt always has to maintain this straight direction. If this pulley gets squeezed in at the same time this pulley gets squeezed in, you're in big trouble. Because A, the belt will get stretched, and B, it'll actually get misaligned. So imagine this guy going in here and this guy going in here. That means our center line will now be from here to here, which is crooked. So it's kind of a geometry puzzle how these pulleys work, but it seems like they're very sensitive to oil pressures. When this one closes in, this one has to come out at the same time. Otherwise, this transmission is just going to blow. So it's very, very sensitive. Now the question is, did one of the seals fail and the pulley collapsed and just snapped the belt? Or did the snapping belt cause no feedback force when the pulley collapsed and blew the seal out? That we can't really answer, but at least we have a pretty good understanding of what it takes to vary these gears using just oil pressure on the sides of these conical pulleys. So the next thing I want to do here is get the remains of this belt off and actually try to lift this big pulley out and explore how the cones move with respect to each other. Where the pressure is applied, what the default position is. Because right now, the pulleys, you can see, they're misaligned and the distance is equal between them, meaning they're both closed. Now I don't know if that's what they do normally or if that's part of the failure. Quick little experiment. I got a pry bar in here against the remains of the belt. I'm trying to push the little segments back into the pulley, and check out what happens when I do that. When I push them in, come on. The pulley actually expands and you can see oil coming out of that hole. Woo! And then I let it go, oil goes back in. So that bottom part of the pulley is going in and out. And let's see, when it's further out, this gets filled with oil. And it's definitely spring loaded to come back in. Okay, so keep that in mind. So personally, I find this the most exciting part of any teardown is to actually figure out how the dang thing works. So in the secondary pulley, just taking some notes, when we force spread it open, oil comes out of the top. So it is spring loaded closed, and the oil pressure forces the pulley to close. If that makes sense. So this pulley is always pinching the belt tight under spring pressure. However, oil pressure actually forces it tighter to clamp the belt, and so there's no slip between the pulley and the belt. And assuming that this is the oil port for for that drum, looking at our cover, you can see that this oil pressure port right here corresponds to this hole over here. And if we blow some compressed air into here, it comes out exactly out of this dowel to pressurize our secondary pulley. That's really cool. So now we can see how the secondary pulley is controlled with oil pressure, and the primary pulley, I think it's the exact same principle, but it's controlled from the back side. And right now it's spring loaded closed, so this drum where the seal is actually rises up towards the bearing, and you can actually see that there's a kind of like a little guide, but I think it's not a guide, it's more of a sensing rod that comes down here, and you see that pin moves up and down. So right now it's in the fully down, pinched closed position, but as that pulley diameter, the distance between the cones grows, this guy lifts up, and that corresponds to a little thing in the valve body right in here. I think that pin goes right in here in this little arm, and that, again, we don't know the exact details, but there's an oil control valve here and an electric motor that retracts or extends this little arm. So, it has to account for all the variables. Where the primary pulley is, that probably feeds back to the secondary pulley to make sure it's synchronized. And the motor, that might be the actual shift motor, to control the gear ratios. It's all like a mechanical feedback system, and obviously with electronic control. So this thing, on paper the concept's pretty simple, but the execution requires a lot of very precise engineering and control. So what I want to do is, again, get these kibbles and bits out of here, and at least pull one of these pulleys and kind of see how it works. So it looks like in these CVTs, the most catastrophic thing that can happen is indeed this steel belt breaking. So there's the remains of the two bands, or two sets of bands I should say. There's still some segments on those, and my magnet tray is overflowing with bits of steel belt. Now let's try pulling the secondary pulley out. Oh my word. So there's that. Wow. Let me get some more bits out, and we can actually see what's going on in here. This is kind of fun. You're going fishing for kibbles and bits. So who wants to guess how many segments there are in this belt? Maybe we'll have a prize. How about this? Whoever gets the number of segments right will get a free t-shirt. And you can't go online and look at a picture and count them either. Alright, we're getting somewhere. Almost done. And I think that's about it, as far as I can see. Alrighty. So now we can actually see some more details. How about this? Here's the primary speed sensor. That got messed up by the carnage, so there's another casualty. We have a little oil squirter here, looks like, that keeps these pulleys lubricated in the belt. And down here is the final drive gear. You can see when you turn that, those gears turn in there. And this secondary pulley is directly attached to this pinion gear, so that there's no other bearings in here. And aha, check this out, there's actually a snap ring holding this drum in place. So if you remember, when we spread this guy open, this part moves over here and this part stays stationary. You can actually see the where the gap is down there. So if maybe we lost a snap ring that goes around here, because the seal, it might have blown out because the snap ring went MIA. I don't know where it would have gone. Might have to look for that too. Okay, next step, I'm going to attempt to pull this primary pulley out. And to do that, we need to take off this little guide mechanism. So the rod pulls out and this whole thing just slides out. So I'll keep that here. And let's see if this guy will just lift up out of here. Wow, it comes apart pretty easy, doesn't it? I heard something jingling in there. So it looks like that speed sensor, I think it was still working as we saw the scan data. But man, oh man. So let's explore this primary pulley. The teeth here are actually what the sensor reads. So that's our primary input shaft speed, or primary pulley speed, I guess. There are these big roller bearings. And there's definitely something in there that isn't supposed to be in there. And the way the oil gets in here, I assume it just comes in through this middle shaft, right through here. We can blow some compressed air down in here and see where the oil squirts out really gently. Don't get sprayed. Okay, this hole right here is our primary pulley oil pressure control. That comes straight from the valve body. And I made a nice mess of my floor again. So I'm curious to maybe take this pulley apart and see what went wrong, if we're missing a seal or what's jingling in there. That might be the last part of this teardown video because we're basically all the way down. The only thing we haven't torn down yet is this clutch pack in here. And that controls I guess the reverse mechanism too, because the reverse gear drives this whole thing backwards even though the engine's still spinning, the right way. So this is kind of similar to an automatic transmission, I think. So the only thing that's different here is the forward gear ratios. That's the separate CVT specific mechanism. I can't believe it, but I actually got this huge 55mm nut loose using the vise, and the vise can't open up far enough to hold this huge drum. So I put a big pry bar in one of the teeth down here, pried it up on boards, used a pipe wrench over here to grab the nut, popped it loose, all for the sake of figuring out what's wrong here. I mean, I could have just sent in the core already, but I'm just as curious as you guys are of what is hiding in this system. So, I guess now we can support this guy with a vise and tap the shaft down, get this bearing off, And hopefully that'll free up this drum mechanism and get that to pop off too. So we're going to try the 3-jaw puller method to get this bearing off. That worked like a charm. No problem. I'm going to set that aside. Now what? Let's see if we even went the right way. Disassembly. My question is, does this big plate just pop out of here or what? It seems like it would. There's no more snap ring holding it in place. I don't know if we can pry at it. Just for safety, let me put this nut back on here just in case it's spring loaded and it's going to explode in my face. I don't there are no instructions. We're just going by common sense approach here. I mean, it has to come off. And this part is stationary, and this pulley moves with respect to this guy. Oh, there goes my pry bar. I'm really not sure. Just for kicks, we're just banging on this plate with a plastic hammer. If it's under spring tension, maybe something will happen. Actually, it looks like that is coming up. Oh. This is really, really, really cool. There's the rest of our seal. That may or may not be the root cause of the problem. Now let's keep prying this baby out. You can always get under there. I don't want to damage anything I don't have to, because, like I said, I don't know if we've gone too far for the core return. I don't know if I can put this thing back together. This thing seems to be sliding up. Damn, I don't want to bend anything here. See if I can get the big pry bar under here and then kind of work around. It doesn't look like there's anything special. Oh, there we go. Ooh. Okay. There's, I don't know, it's like empty, but we have these metal bits in here. I don't know where the heck those came from. That explains our rattling sound. However, there's no groove for a circlip like we had on the secondary pulley. So this guy just kind of hangs out here, and you can see how this pulley actually slides in these grooves. There's a chunk missing there, I think. This is all scoured up right there. This might be part of our problem. What are all these little nibbins? Well, the closer you look, the more you understand. So, let's see. These grooves right here. 1, 2, 3, right? I think they're supposed to line up with these corresponding little half moons 1, 2, and 3. So what happened was, this pulley, for one reason or another, actually rotated with respect to our shaft. It's not supposed to rotate, it's only supposed to slide up and down axially. But it actually rotated with respect to the shaft. It sheared off whatever goes in those little grooves. Like little, they might be little balls to keep this thing, you know, in line with the shaft here. So that's where all those little pieces came from. And there's a spring right there that keeps the balls from, you know, coming out of their respective holes. So what I think we need to do is try to keep the shaft fixed and rotate this pulley back to, you know, its corresponding groove here. And I'm not exactly sure if it's just supposed to slide up, because right now I think it's just jammed because it sheared those metal things in there, and they're jamming the pulley against the shaft. So if we can try to unjam it, turn it here, I think since these grooves are just free, this pulley should pull right off of here. And, you know, looking at the system, this dome is the actual oil pressure chamber. So this thing fills up with oil through the holes. The feed is, you know, from the bottom, from the torque converter side. This thing gets filled up with oil, and it presses this pulley down against this pulley. So I guess pretty simple system, but this wear pattern right here in these grooves, I think that's what killed us here, because that's not going to be a catastrophic failure. That was gradual, you know, wear, and you can see where the ball stops. See how that's all chewed out, and up here it's fine. That's how far this pulley could extend. So basically, it almost looks like, you know, the metal is too soft or something, because again, the fluid is lubrication for everything here. It really is. But keep in mind, the entire power from the input shaft is going through this shaft and transferred to the pulley and to the belt to drive the secondary pulley. Now, that huge torque is going on these little tiny balls, because if they weren't there, this pulley would just rotate with respect to the shaft. So even if you change your fluid, I don't think it's going to prevent this from happening. So they either used, you know, little ball bearings that are too tight. Maybe they should have more of them on here instead of just 3 grooves, have like 6 to distribute the load more evenly. So we're finally getting to the root cause of this CVT failure. It was not the belt catastrophically failing which caused the whole problem. I think it was this pulley which finally gave out, spun on the shaft, which it wasn't supposed to do, and that, you know, that like sheared the belt, and that was it. Then you have no more action. And you can even see on here that if you look down this groove, this side is more worn than this side. Would that make sense? So if you look at the transmission, so like this, the engine is spinning clockwise, right? So this shaft is spinning that way. I guess if you look from this side, it's counterclockwise. So keep that in mind. So same thing here. This shaft is spinning counterclockwise, and it's the ball would actually be jammed to this side and spinning the pulley the same way. So absolutely that makes sense. This side is more worn out. Same with this side, it's all symmetrical. This side's worn out. Same here. So that is how the CVT fails. And I assume that this is unavoidable. Even if you have the best lubricant, the pressure on that ball is just so great, and it rides not only, you know, it goes this way, and it transfers an immense amount of torque from the engine to this pulley. That is crazy, but I think it's just inherent in the design. They should make these grooves bigger. They should put bigger balls in there, maybe more balls, to distribute this you know, extreme torque. I can't imagine what would happen if you're towing with this thing, you know, in the city. It probably wouldn't even last 100,000 miles. So we're gonna try our best to get this pulley off, and but that should be it. So we can also use the same 3-jaw puller. Try to get this drum off. Let's put it on the low setting. See what happens. Alright, so inside the pulley we can see more little sheared pieces of whatever is supposed to keep it from turning. There, little nuggets. And looking at these grooves on the pulley, actually they look fine. They don't look worn out at all. See that one? No problems. But as we look on the shaft, there's where the problem lies. Boom. That guy is chewed up. So that was a long-term wear. And eventually, those little nuggets, they had enough and exploded. This one's really bad. Wear on the shaft. This guy is just kind of wide. Yikes. So I would say this is an inherent materials flaw and design flaw, that, you know, the shaft, the metal here is a lot softer, it seems like, than on this pulley, and that's it. That's what happens. Something wears out. It's not a lubrication issue. This is just overload of these bearings. So it's not rated, you know, for this amount of torque, this many miles, I guess. See, that metal is just like sandwiched. Yep. So hopefully they redesigned some of this to last longer, but you never know until you take the next one apart. But I think we'll wrap it up here. I don't know if I can put this thing back together and get my cord charge back, because if they see that everything's been torn apart, I mean, this is pretty much junk. They need to replace this. Replace the whole pulley set, replace the belt. I guess the valve binding might still be good. So for the reman process, I don't know what parts they keep, what parts they reuse, and what gets renewed. But anyways, I hope the 99-cent paid fee was worth it. I kind of felt guilty, making it a paid video, but this is just, it takes time, and the $800 core fee, I won't even know if they'll accept it until like a month down the road. So if they do, there'll be a little bonus, but if they don't, hopefully the views will cover this part of it at least. So I really appreciate you guys watching. Stay tuned for more. This is really exciting stuff, new tech. We'll keep tearing into it and diagnosing and getting to the root cause of the problem. That's what this channel is all about, and I really enjoy kind of exploring, learning, and sharing it with all of you. So thanks for watching. I'll see you next time. Bye-bye. Just a little bit of bonus footage here. So I put this thing back together, and now the top half of the pulley actually slides in and out since it's not jammed up by those little nuggets anymore. So there's no spring-loaded part on this primary pulley like there is on the secondary, and that is by design. So when the car's off, there's no pressure in here. The secondary pulley squeezes the belt, so we get to this scenario here. This squeezes together, the belt rides up, and then there's no pressure here, so these pulleys spread apart. And what ratio do we get? We get first gear, or low ratio. So that's kind of the default. When you start the car, you're in low gear, like you want to be. And then as you accelerate, the pressure gets fed in by the valve body through here, and this thing starts to squeeze the belt and come down. So gradually we transfer to this scenario right here. The primary pulley squeezes the belt, it starts riding up higher and higher, and the secondary, I assume, lets go of the pressure, and the pulleys actually spread apart. The belt spreads apart those internal springs, and we get to this overdrive or highway high speed. So not too bad of an analysis, I think, without having any real direction or instructions. Just observing how the system's put together, we can kind of get a very good idea of how it works. So that's all I wanted to point out here. So I got the pulley set back in place. This is the secondary that spins our drive gears, and our primary. Now I'm wondering if I should stuff this old belt back in here and kind of sprinkle this whole mess around, just so kind of make it look like we weren't even in here. I'll think about that. This drive belt here, really a feat of engineering. Oh, and these plates, so this thing can bend and flex. I think that's kind of amazing that this whole thing just keeps going and going and going for miles and miles and miles. So the engineers did their homework on the belt, I think. That was not our original problem. Not at all. So those pulleys are always supposed to be aligned, and if one pulley moves with respect to the other, this whole belt it gets like torqued, and that's where our issue came from. But again, who wants to guess how many pieces there are in here? They have little locating pins, and the shape of them is actually designed so they can flex like that and go around and then straighten back out. Neat stuff. I almost feel bad doing this, but we gotta put this back in there. Oh boy. Hope it fits. Sprinkle, sprinkle. Maybe I should give these out as souvenirs. The CVT Teardown special. Terrible.